Atoms, elements, and isotopes in a nutshell. So what are they and why do we care about them? Well, atoms are just the building blocks of everything. Elements, when you have a whole bunch of atoms together, they together make up the identity of the element. It's basically the components of an element, the parts that make up the element. Isotopes are basically different variations of a specific type of element, and we'll talk about all three of these in detail. So let's get started. So what's the structure of the atom? So the atom is basically composed of a nucleus, which is the inside right here, that has protons and neutrons. And we have outside of that are electrons and what's called electron shells. That's what we're going to look at right now. Eventually we'll realize they're actually in what's referred to as clouds, but we don't want to complicate it right now. If you look at the relative sizes of the particles, you can see the protons and neutrons are fairly large compared to the electron. Protons are positively charged, neutrons are neutral, and electrons are negative. In terms of mass, protons and neutrons are pretty similar in mass. Electrons are extremely small or negligible in mass. So we actually consider the mass of it almost being zero. We pretty much ignore it. The thing you need to understand is that the protons and neutrons are inside the nucleus. They make up all the mass of the atom. The electrons are on the outside rings. And based on how many electrons you have, that tells you how big the atom is. Because the distance from the nucleus to the outermost electron represents the size. So more electron rings means bigger atom. That's how the size comes into play. So two different things. Mass is due to the nucleus, which by the way is extremely small. How small? It's like putting a marble in the middle of a national football stadium. That being the nucleus, the marble, and the rest of the football stadium, an NFL one, not a high school one, representing the rest of the atom. So it's extremely small, but it makes up all the mass. So it has a nucleus, contains protons and neutrons. There's an electron cloud outside the nucleus where electrons exist. And we're going to refer to these clouds as shells or rings for now. And we're going to assume they're going in orbits around the nucleus, kind of like the planets around the sun, even though that's not really what happens. But for our understanding right now, it's important to have a basis for how to look at an atom. And right now we're going to look at it in that fashion, and then we'll evolve later. Our subatomic particles, protons have a positive charge, as I mentioned, and has a mass of 1 AMU. What's an AMU? It's a unit of mass specific to atoms. They're so small, and the mass is so ridiculously small that they created their own unit system. So it represents atomic mass units, and that's basically the mass of the atom. That's what we use to represent atoms in terms of subatomic particles, which are your protons, neutrons, and electrons. Electrons have a negative charge and a mass of 0 AMU. Like I said, negligible to 0. We just call it 0 because it's easier. Neutrons or neutron have a mass of 1 AMU, so you can see the protons and neutrons are similar in mass. Conceptually, what you want to understand is that positive charges repel. So that means two protons near each other will repel. And somebody was like, wait a second, isn't the nucleus composed of protons? Yeah, it is. But you have neutrons in between, which helps shield that positive charge from being too much of an impact. So that's why the atom's still able to stay as an atom, because you have neutrons in between, blocking those positive charges, repelling the protons from each other. Negative charge repels. That means that even in the shell or ring that the electrons are located, they're going to try to stay far away from each other. And unlike charges attract. This is the reason why we have an atom to begin with. If the nucleus wasn't positive and the electrons were negative, there's no reason for the electrons to stick around the nucleus. There's nothing. There has to be some sort of attraction, and that's where the opposite charges coming in is important. Information you get from the periodic table. So the top number is your atomic number. That's our number of protons. So this is our protons. For a neutral atom, that is also your electrons. Same number. I say neutral because we're going to talk about ions. Ions are atoms that have a different number of electrons than protons. So atoms lose or gain electrons, and that creates ions. As a result of that, the number of electrons for atoms can vary. We'll talk about that later. But for now, if it's a neutral atom, you assume the top number is your protons and your electrons. Not combined, each of them are 10, because the atom has to be neutral. 10 protons, 10 electrons. You have the symbol, you have the name, you have the mass. These masses are because isotopes exist, and we'll talk about that in a little bit. We'll come back to. And this electron configuration, we'll talk about electron configuration much later. So the atom has 10 protons, 10 electrons, and 10 neutrons. So let me point out the last thing. So to get our neutrons, because we can't have a decimal for protons and neutron number, we round numbers up and down. In this situation, you look at 20, you look at the number after the 20. If this was 0.5 or 0.6, anything at 0.5 or above, you'd round this up to 21. So that's the mass you would use, 21. Here is 20.1, so it's going to call it 20. So we're going to ignore the decimals altogether, so our mass is 20. Now, why do we do that? To get our neutrons. Because I told you your protons and electrons are this basically your atomic number. So what are your neutrons? It's this minus your top number. So when you subtract those two, you get your number of neutrons. So 20 minus 10, which gives me 10 neutrons. That's how you figure out your neutrons for any element. You round the mass to a whole number, then you subtract it from the atomic number, that's your neutrons. For those wondering why, because we know protons and neutrons make up the mass. The mass represents protons plus neutrons. So if I have the total and have the mass of one of them, I can figure out the mass of the other by subtracting. Size of the atom, as I said, is based on how far the first electron is. The outermost electron has a specific name. It's called the valence electron or electrons. So your valence electrons are electron in your outermost ring. So if we have, let's say this is your nucleus, let's see, you have this, let's assume there's 2 electrons here. Let's assume there's 4 here. This has 4 valence electrons. Why? Because there's 4 electrons in the outermost ring of the atom. That's what valence means. Electron in the last ring. And as a general rule, in case you're wondering, your first ring can hold 2 electrons. So that's our first ring. Sorry about the oval. Everything afterwards is going to hold 8. So first ring 2, everything else 8. We'll find out later that's not really true, but for our purposes right now, it works. So we're going to assume the first one has 2 electrons. All the other rings have 8. So that's how you can figure it out. So if an atom has, let's say, like oxygen, which is a total of 6 electrons, 2 of the electrons would be in the first ring, and 6 would be in the next ring. Give us a total of 8 electrons, like we would expect for oxygen. And in this situation, we have 6 valence electrons, 6. The mass of the atom comes from the number of protons plus the number of neutrons, as we said. All right, isotopes. What the heck are isotopes? Isotopes are different variations of an atom. So it turns out every atom has twins and triplets, if you will. Basically, they look alike, but there's a difference. What's the difference? The number of neutrons each of them contains. Because the neutrons changes, your mass changes too, right? So the mass of this is 1, the mass of this is 2, the mass of this is 3. All I did is add my neutrons and protons together. Electrons stay the same because that doesn't get impacted. But your protons and neutrons, your protons have to stay the same always, because if you change your protons, you change the identity of the element. So it changed the number of neutrons. So these are different isotopes of this element. So what's the element? Hydrogen. How did I figure that out? What has an atomic number of 1? Because that's how many protons it has. That's right, hydrogen. So these are all different isotopes of hydrogen. You can see the difference between them is that this has 0 neutrons, this has 1 neutron, this has 2 neutrons. So these are called isotopes. When they have different number of neutrons and different masses, it's an isotope. I should say one more thing before we step away from this page. The reason that the mass and the periodic table are decimals is because what they do, they take the abundance, how common it is in nature. Let's just say that 20% of all hydrogen is, let's go 70, is this. Let's assume 10 is this. We'll make this 20. And 10 is this. The way they figure out the mass in the periodic table, the numbers they got, they multiply the percentage times the mass. So 0.70 times 1. And then 0.20 times 2, which is 0.4. And 0.10. And where do I get the 0.10? When you change a percent symbol to decimal to calculate, just move the decimal point 2 times to the left. So now you can do the calculation in your calculator pretty easily because you just already have it set up. So 10% of 3 is 0.3. So these numbers are completely inaccurate because This gives me 1.4 as the mass in the periodic table for hydrogen. We know it's 1.008. So my number choices were horrible. This should have actually been probably 95% of this, and maybe 4 and 1 or something. But the point is, that's how they got the mass in the periodic table. They take the percentages present in nature, multiply times mass for each one of them, add them all together, and that's what you see in the periodic table. So periodic table's decimal is because of this. Because 1 plus 1 is 2. So what the hell? If a proton weighs 1 and a neutron weighs 1, how do you get decimals? This is how, in case you're wondering. All right, there's different isotopes. You can see lithium has 6 and 7. And if you're wondering which isotope is more common in nature, look at the mass. The mass is 6.9. So that's closer to the isotope that has 7. So the majority of lithium is actually 7, has a mass of 7. And that's how you can do it for anything. Just look at your actual mass and look at which isotope is closest to it, and that's what the most dominant isotope is. So in this one, carbon-12 is. This only has 1 variation, so there's nothing fancy going on. Oxygen, you have 3, so which was the most common? It's actually like 15.99. Let's round it a little too much. But you could regardless tell that oxygen-16 is the most common form of oxygen in the world. These 35.45, well, you would assume it's somewhere between here and here, right? So that means these two are the most common. And that's how you can figure it out for all of them. But every element has different isotopes. Magnesium has 3. And just to show you how the numbers are impacted by that, see, the number of electrons are the same for all of them. So is your atomic number of protons. Those don't ever change for isotopes. What does change is your mass. Why does your mass change? Because look at your neutrons. You're going from 12 to 13 to 14, and guess what happens to your mass? It goes up 1 each time. So let's try some questions. An atom of zinc has a mass of 65. How many protons does it have? Well, I have to look in the periodic table. And if you look in the periodic table, zinc's atomic number is 30. So that is your answer. How many neutrons are in a zinc atom? Well, your mass is 65. You have 30 protons, so you would expect it to be 35. Because remember, subtract the mass minus atomic number, and voila, you get your neutrons. That's how you always figure it out. What is the mass of zinc atom? That's 37 neutrons. Well, we know our atomic number can't change, right? So your atomic number is always going to be 30. You have 37 neutrons. So your total mass is going to be the addition of those two, so 67. All right, atom has 14 protons and 20 neutrons. Atomic number is, all you have to do is look at the protons. That's your atomic number always, period, end of story. So in this situation, it's going to be 14. Its mass number is, well, your mass is going to be protons plus neutrons, right? 20 plus 14 is 34. The element, how do I identify the element? Look at the atomic number, or your protons, and that's going to identify. So in this situation, it's silicon, because that has atomic number 14. The atom is bigger than, well, it's silicon, so it's bigger than. It's going to have more shells than which element? Well, if you look in the periodic table, it would be lithium. Lithium only has 2 rings. Silicon has 3 rings, so obviously silicon's going to be bigger. And by the way, the way you figure out how many rings an element has is based on its period. So anything in period 1 only has 1 ring, period 2 has 2 rings, period 3 has 3, period 4, 4, 5, 6, 7. And for those wondering what the heck is a period, it's the row. So a horizontal row is a period. So if you look in the periodic table, you have 7 periods, and then you have 2 in the bottom that have been removed from period 6 and 7. So you have only 7 periods in the periodic table, so you only have 7 maximum shells possible based on the elements we've discovered. All right, so let's talk about nuclear symbol. So usually when we're trying to represent an element, we represent it with symbology. This is called the atomic symbol for it, or nuclear symbol. What it tells us is some information. So your mass numbers in the upper left, always. Your atomic numbers in the bottom left, always. So it's the opposite of the periodic table. For those that are going to think you're going to get confused, just remember the biggest number is always going to be your mass. Whether you look in the periodic table or when you look in the symbology, the bigger number has to be your mass, right? There's no question about that. I do want to point out that sometimes you'll see elements with charges, and the charge will be in the right-hand corner. And also, when we're doing formula writing, we will put subscripts, and we'll talk about that later, so I'm not going to confuse you right now with it. But for now, just understand that this is the typical way an element is represented: mass on the top, atomic number on the bottom left, charge on the upper right. And the charge in this situation, we know that this thing has 11 protons, right? So how to get a positive 1 charge? It lost an electron. So now we have one positive 1 charge. You have one more proton and electron, so that's where the positive 1 comes in case you're wondering. But we'll talk about that later. All right, nuclear symbol indicates the number of protons, neutrons, and electrons. So let's go through this real quick. So oxygen has 8 protons, right? That's the bottom number. 8 electrons because the atom is neutral. So your neutrons is 16 minus 8, which is 8. So everything is 8. For this one, you have 15 protons, 16 neutrons, 31 minus 15, 15 electrons, done. Zinc, your protons and electrons are 30. Your mass is going to be 65. So 65 minus 30 gives my neutrons, which is 35. Let's try another one. All right, for this one, how many protons? 6. How many protons? 6. Protons, 6. Same number. These are isotopes of carbon, so they should all be the same. Neutrons, 12 minus 6 is 6. 13 minus 6 is 7. 14 minus 6 is 8. Electrons, 6. Remember, protons and electrons are the same. 6 and 6. Write the nuclear symbol for an element with the following subatomic particles. So 8 protons, 8 neutrons, 8 electrons. Well, all I have to do is look at the protons and its identity. So that's going to be obviously oxygen. 17 protons is going to be chlorine. And 47 protons is going to be silver. So the atomic notation, the bomb number was 8 for oxygen. Your neutrons and protons add together is your mass, which is 16. And the electrons really is not relevant. Unless they're different, it doesn't make an impact. If they're different, the protons and electrons, then you get charges, but these don't have it. So that was the different variations of isotopes, atoms, and ions, at least the basics of it.